In this video, we will do some examples that involve determining whether we use permutations, combinations, or other counting methods. So let's get into an example right away, which says, how many ways are there to rearrange the letters in the word Mississippi? So I want to talk about two ways we can solve this. So in this first way, I want to notice that there are 11 total letters here. 11 total letters that we're rearranging. So let's imagine that there are 11 empty slots, and we need to fill these empty slots with these letters. Okay, so I'm just going to draw these slots. So slot 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So one of the things I need to sort of think about is, well, there's a few different types of letters. Like I see the letter M, I see the letter I see the letter S, and I see the letter P. So I see 4 different letters here. And, if I were to switch like 2 of the S's, for example, the word still looks the same. Or if I were to switch 2 I's, the word still looks the same. So what I can do is, I'm going to break this down into different steps. Maybe I can first place all of the S's. I'll put this in quotes. Place all the S's, then all of the I's, comma, then all of the P's. It doesn't really matter which letter I do first, then all the P's, and then all the M's. Then all the M's. And yeah, so I could do this in any order. So can go, which one I decide to place first, it doesn't really matter. I can go in any order here. All right, so maybe I'll focus on the order that I've just listed. So maybe I'll first place the S's. I'll first place the S's. So I have to place 4 S's in 11 slots. And to do that, well, I got to choose 4 of the 11 slots to put the S's in. And the order in which I pick the 4 slots doesn't matter. So if I were to pick this one, and then this one, and then this one, and then this one, well, that would have been the same as if I had picked this one first, and then this one second, this one third, and this one fourth. Because either way, 4 S's are going to go in them. So the order in which I pick these 4 slots to place the S's in does not matter. So that's an indicator I'm going to use combinations. So there's 11 choose 4 ways to choose 4 slots for the letter S. So notice that the order they are placed doesn't matter. Order they are placed doesn't, and that's why we're using combinations. Doesn't matter. Okay, then I'm going to do something similar for each of the remaining letters. So now maybe I'll place the I's. So for the I's, well, we have 4 of them. There's 4 I's. Well, now that we've placed all the S's, there's just 7 remaining slots. Because 4 of the slots already got S's placed in them in this first step. So how many ways are there to do this? Well, there would be 7 choose 4 ways. 7 choose 4 ways to do this. Again, the order doesn't matter in which I place these 4 I's into those 7 slots, because ultimately there's just going to be 4 I's. All right, and then after that, let's pick the next letter. So maybe now I'll place the P's. So for P's, there are 2 P's that can go in. Now there's 3 remaining slots. There's 3 remaining slots. So we can do this in 3 choose 2 ways. I'm choosing 2 of those slots, choosing 2 of the 3 slots in which I place the letter P into. All right, and then finally, I place the letter M. So we place M. And there's just one M that goes in one remaining slot. One remaining slot. Okay. So, I might just be able to see quickly, well, that's just one. But if I use my combinations, I would be doing one, choose one. And if I worked out what this equals, this does indeed equal 1. So there's one way to do this. All right, so I have the number of ways for each of these steps. So now to put it all together, we multiply these quantities. So the total number of ways to rearrange the letters is 11 choose 4 times, what is it, 7 choose 4 times 3 choose 2 times 1 choose 1. Okay, and for a problem like this, it would be totally fine to leave my answer like this. If it did ask me to simplify it a little bit and just express it in terms of factorials, let's briefly talk about what that would look like. So if I used my formula for, n choose k, 11 choose 4 would be, it's 11 factorial, then I divide by 4 factorial, times, and then it's 11 minus 4 factorial. Remember, that's our formula for n choose k that we saw on the last video. Remember, the formula for n choose k is it's n factorial over k factorial times n minus k factorial. Okay, so if I do that for 7 choose 4, I'll get 7 factorial over 4 factorial times 7 minus 4 factorial. For 3 choose 2, I'll get 3 factorial over 2 factorial times, and if I do the same thing, I'll get 3 minus 2 factorial, which is 1 factorial. And for 1 choose 1, I will get 1 factorial over 1 factorial times 1 minus 1 factorial, which is 0 factorial. And let's go ahead and simplify some of these other ones. 7 minus 4, that's just 3, so I'll get 3 factorial here. And then 7 minus 4 is 7, so this will be 7 factorial down there. 7 factorial. Okay, so I can simplify this. I can simplify this more. I notice that 7 factorial and 11 factorial will cancel out a bunch, and it'll just leave me with 11 times 10 times 9 times 8 up top. That'll cancel the total 7 factorial. And on the bottom, I'll still have 4 factorial. I can similarly cancel the 7 factorial a little bit with this 3 factorial that I have second. That'll leave me with 7 times 6 times 5 times 4, because the 3 factorial part at the end gets canceled, and that'll leave me with 4 factorial at the bottom. I could do the same thing with 3 factorial and 1 factorial to get 3 times 2 over, that'll cancel the 1 factorial then. That'll cancel the 1 at the end. And I still got 2 factorial on the bottom. And then finally for this last one, well, I noticed that 0 factorial is just 1. So 1 times anything is just the anything. So this last part up top, I can just keep it as 1. And on the bottom, I'll get 1 factorial. So if I multiply this all together, I notice on the numerator, I get 11 factorial. All over, on the denominator, I got 4 factorial times 4 factorial times 2 factorial times 1 factorial. So I didn't have to do that, but I'm doing it just to show an example of how I might simplify this if I needed to write my answers with factorials. And also, I'm going to solve the problem in another way now, where we'll actually show how we can get this more quickly. Okay, so that's the first way I can do this. Let's talk about another way, which is, what if I started off by just permuting all 11 letters? But then notice that, well, we're going to overcount, and let's adjust for overcounting. So there's 11 letters in this word. So there's going to be 11 factorial ways in which I can just permute those 11 letters and rearrange them. But this overcounts a little bit. This overcounts because, for example, it would consider something like M, and then let's focus on the I's. I'll call the first I, I1, and then I got S, S, and then I'll have another S, S, and then a P, and then a P. I'll call the next I, I2, and the next one I3, and the next one I4. This permutation is considered We want to consider this the same. Ooh. We want to consider this the same as if I had M and then SS. Oh no, another SS, whoops. Another SS, then a PP. All right, and then let's switch the order of the I's a little bit. So let's say that this was I3, and then I had I1, and then I had I2, and then I had I4. So for our purposes, if we switch the I's around, that's the same word. This is still Mississippi either way. But when we do 11 factorial actually would count these as different. So we want to consider these to be the same, but 11 factorial counts these two things as different. Okay, so let's see if we can adjust for this overcounting. So in a given permutation, let's think about, well, how many ways would there be to reorder, each set of letters, and then I'll adjust for that overcounting. So we can reorder the 4 I's that we were focusing on here. Well, how many ways? Once I've picked a position like this, how many ways are there to just swap the 4 I's amongst those spots? Well, I could do that in 4 factorial ways. Okay. And then what about for the S's? The 4 S's similarly in 4 factorial ways. There's the 2 P's, the 2 of the letter P's. Those, we can switch their spots in 2 factorial ways. 2 factorial ways. And there's only one M, so I don't have to do anything with the M. But if I really wanted to be thorough, maybe I'll put this in parentheses, and I would say the 1M in 1 factorial ways. It turns out I don't really need this because 1 factorial will be 1. So if I divide by 1, it won't change anything. But I'm just writing that there just in case. Okay, so if I put this all together now, my final answer would be, well, I started off with this 11 factorial. But then I got to divide by these factors that we're overcounting by. So because I can reorder these I's in 4 factorial ways, we got to divide by 4 factorial. And then I can reorder the S's in 4 factorial ways, so I divide by 4 factorial there. And then for the P, I divide by 2 factorial. Okay, and that's my answer. So I'm going to box this. If I wanted to also divide by 1 factorial for the M, I could, but 1 factorial is just 1. 1 factorial just equals 1, so whether I include it there or not doesn't really make a difference. But I want to notice that, wait, this is the same thing that I got for the last problem, which is kind of nice. This example also illustrates that sometimes when I solve counting problems, there can be multiple ways of arriving at the answer. And it's helpful to be able to think through those so we can identify the most efficient way. Because I would say that this was the most efficient way of getting to this answer. Although the other way worked as well, it was just a bit longer. Okay, so let's tackle another example. All right, so this next problem talks about hands in poker. So it says that a standard deck of 52 cards has 4 suits, and the 4 suits are spade, diamond, heart, and club. And each of those suits has 13 what are called ranks. So the ranks are, we sometimes think of those as the numbers on the cards, which are 2, 3, 4, up until 10. And then there's some cards called the jack, the queen, the king, and the ace. So if you're not super familiar with cards, that's okay. The key thing that we need to know is, well, these 52 cards are split up into these 4 suits, and each suit has 13 different ranks. And then the problem says a poker hand has 5 cards. Part A says, how many total poker hands are there? How many total poker hands are there? Okay, so in a poker hand, we have to choose 5 cards out of the total 52. And when I do that, the order in which I pick the 5 cards doesn't matter. Order I'm going to put this in red. Order doesn't matter. And because order doesn't matter, we use combinations. We are going to be doing 52, choose 5. And that's my answer. It's totally fine to leave it like that. If we did want to work this out, it turns out that this ends up becoming 259,8960. So it's a huge number. There's a bunch of different poker hands. Okay. And the way I could get this is I use that formula for my combinations. And we reviewed that a little bit earlier. Okay, but totally fine to leave my answer just in this choose notation. The same is going to go in our homework problems. In general, it's going to be okay to leave it like this, especially when the numbers are large. Okay, so part B now asks, how many poker hands are full houses? And a full house is when you have 3 cards of one rank and 2 cards of another rank. So for example, if I had 3 5s and 2 queens, that's a full house. Or if I had 2 4s and 3 7s, that's a full house. Okay, so for this, I want to give you an opportunity to try it and think about this first. So pause the video for about 4 minutes to try this. This is the most important time, I think, of these videos, the chance where you can try these problems. It's a great way to assess, well, how well do you understand how to do problems like this on your own? Pause in 4, 3, 2, 1, and try it. All right, so hopefully you did that. Hopefully you paused it to try it. Let's talk about it now. So let's break this down into steps. So one thing I'll have to do is I'll have to choose the rank of 3 cards. There's some rank that I'll have from which I'll have 3 cards for it. Like for this one is the 3 5s. For this one is the 3 7s. So I'll have to do that. Choose the rank with 3 cards. And then maybe after that, then I'll choose the rank. I'll choose the rank from which we have 2 cards. Like that was the 2 queens from this one, or the 2 4s from this one. So let's break each of these down. So when I choose the rank with 3 cards, well, there's 13 total ranks. So there are 13 ways to choose a rank. 13 ways to choose a rank. I'm picking one of these 13. Okay, and then once I pick that rank, like let's say I pick the 3 as the rank. Well, there's 4 total 3s because there's 1 in each suit. So I got to pick 3 of those 4. So how many ways are there to do that? The order in which I pick those 3 of them doesn't matter. So I would be doing 4 choose 3. I use combinations. There's 4 choose 3 ways to then choose their suits, because there's 4 total suits and I'm picking 3 of them. So in other words, I'm picking 3 out of these 4 cards. Okay, and if I worked out what 4 choose 3 is using my formula, well, it's 4 factorial over 3 factorial times 1 factorial. So this becomes 4 times 3 times 2 times 1 over 3 times 2 times 1 times another 1. 3, 2, and 1 cancel with this 3, 2, and 1, and I just get 4. Okay, so this ends up just being 4. Cool, so we're halfway there. Now let's do the second part. I got to choose a rank that has 2 cards in it. Well, I've already picked the rank that had the 3 cards, so the one that has 2 cards, it's got to be different from the first one. So that means, well, I've already picked one of the 13 ranks from which I pick 3 cards. So there's 12 remaining ranks. So I got to pick one of those. There's 12 ways to choose this rank. It's got to be one of the remaining 12. Okay, and now once I've decided on what that remaining rank is, like maybe it was all the 8s, maybe it was all the 8s. Well, now I got to pick 2 of those 8s to select. And the order in which I pick those 8s doesn't matter. So I'm going to use combinations. I'm going to be choosing 2 out of those 4. 4 choose 2. There's 4 choose 2 ways to choose their suits. So let's work out what 4 choose 2 is. So 4 choose 2 would be 4 factorial over 2 factorial times 4 minus 2 factorial, which is 2 factorial. And if I simplify this, I can cancel a little bit with the 4 factorial and the 2 factorial. It'll cancel the last two terms. So I'll get 4 times 3 divided by this 2 factorial. And that's 12 divided by 2, which is 6. Okay. That's what 4 choose 2 is. This is what 4 choose 3 was. So my total number of full houses is going to be, there was 13 first, and then times the 4, times that 12, times the 4 choose 2, which was 6. It's fine to leave my answer like this. If I wanted to multiply it out and work it out, this ends up being 3,744. And there we have it, our number of full houses. So one of the nice things that these counting tools will let us do is determine things like this. Determine, well, how many poker hands are there that fall into this special category? And among other things, that lets us figure out like probabilities in poker.